equation, which is A2 plus B1. And using these 4 equations, I can solve 4 variables: B1, A1, B3, and A2. So from these equations, I can solve these 4 variables. Yes. So I can achieve that using 1. But my animation is showing 2. That's right.
So you need to be able to control your quantization, right?
Yes. So this
is just an information theoretic point of view.
Yes.
Right. This is not an implementation.
So you're also thinking about implementing this scheme.
Yeah, that's right.
And just thinking. So we're using your regular ADC, which does the quantization. So how would you see?
So you
can discuss it after
the
rotation.
Yeah. So you can think of it's like you can do a quantization, and then you can map this one. You can furthermore channel codes this quantity. That's one possibility. So I don't know. So for transmitter operation, you can observe a very interesting duality among the. So for transmitter operation, this is like a downlink scenario in the server networks, right? Because it's like the base stations, they are cooperating, which base stations are serving as transmitters, and the transmitters are cooperating. So this is like a downlink scenario. And you can observe a very interesting uplink-downlink duality in this in this problem. So I'm going to I would like to go through this example, which is the dual of the examples in the receiver cooperation case. So in this example, each transmitter is allowed to convey 1 bit of information to the other transmitter. And you can think of this exchange information is going to be served as precoding site informations. Site informations for precoding. And you can use this precoding to cancel the interference. And you will observe the same kinds of behavior, which is either 1 by 1 or 2 by 1. So in this kind of observation, we have uplink downlink duality like this. So it's very simple that you just reverse. So for the uplink receiver cooperation, we can derive the corresponding dual downlink channel. It's just you reverse every arrow, and then you take the conjugates of the channel gains, and then you exchange the receivers and the transmitters, and then you obtain the downlink transmitter cooperation channel. Okay? And there's a theorem that in the linear deterministic channel, there's a there's a downlink and uplink duality among the Shigorari regions, and we're conjecturing that it's also true in the Gaussian channel. So this is a summary for the state of the art of this interference channel with orthogonal cooperation. So when K is the number of users, and I use the solve is in the sense that the capacity region is characterized to within a constant number of bits. This constant is not scaling with the channel parameters. It's only a constant universal. It's a universal constant. So I solved the K equals to 2-user interference channel with receiver cooperation. And for 2-user transmitter cooperation, I have some capacity results, but I'm still working on the capacity region results. And for more than 2 users, it's wide open because even for the 3-user interference channel, the capacity is quite open. What else can happen? Right. So I want to talk briefly about the. So this is the current work, and the following are the future works, which I proposed in my exam. So for resource allocation problem, so I'm moving from physical layer to mechanical layer, basically. And now the resource is not only the time frequency resource blocks in the audio systems, but also the backhaul link capacity. Because we think of these backhaul links are limited, so they are also serving as kind of resource. So the conventional interference management, in my understanding, is that the resource is only the time and frequency resource blocks, and basically we're hopping over the frequencies over time, cross frequencies over time, to get the interference averaging. But we are still treating this interference as noise, treating this intercell interference as noise. Okay? And the principles for interference management is treat interference as noise and doing orthogonalizations inside the cell, using orthogonalization over subcarriers. Now, the paradigm of cooperative interference management in this proposal is that the difference is that we have one additional resource, which is the backhaul link capacity, and we want to use a new principle, which is partial interference cancellation. So we need to, like what I said in the previous works, in the previous slides, we need to know the channel state equations and the transmitters. Okay, and also from the previous analysis, we know that the coefficient gain varies with channel strengths. So you can think of that an optimization problem that given these channel gains, how do I distribute this backhaul capacity so that the total throughput is maximized, for example. And in downlink, there's one additional dimensions to be optimized, which is the transmission power allocation. So here's a very simple example to illustrate the optimization problem on the line. So let's say that for resource block A, we have these 2 users in 2 cells, cell 1 and cell 2. And between these 2 base stations, I have a backhaul capacity link. Backhaul link with capacity C. So let's say for resource block A, the underlying 2-user interference channel is symmetric. So I have SNRA and NRA. And the sum capacity for these 2 users is going to be a function of SNRA, NRA, and the channel link capacity CA. And the backhaul link capacity CA. CA is the backhaul link capacity dedicated for this resource block.
The subscript A is there for what reason? For resource blocking.
Yes, for resource
Because everything is the same. So otherwise everything's symmetric.
Yes.
Say that again.
So I assume that, for simplicity, I assume that for this resource block A, everything is symmetric. So I can draw.
So it changes from resource block to resource block.
Yes.
Yeah.
But CA and you'll see that CA and CB, they're partitioning the backhaul link capacity C, the total backhaul link capacity C. So system throughput. Let's assume that this is a very
What
simple
is this
example.
now? The B guys.
The B guys are
So we have 4 terminals?
yes. So assume that this is a base station serving 2 users in each cell, and so now I have only 2 resource blocks. And these 2 users use this 2 resource block. But because I'm assuming 4 frequency reuse, so this
Okay,
resource
I
block
got
will
it.
be
So you're assuming that two users in a given cell are not
The
interfering.
blue,
Yes.
the blue guys
So-
and the red guys are